Welcome to the Explainer. What if a math problem, one that's been considered unsolvable for literally centuries, just wasn't anymore? Today, we're going to look at a brand new theorem that makes a pretty bold claim, that it can solve equations once thought to be completely impossible to solve exactly.
So let's start with a big question, one that's kind of been bugging mathematicians forever. We all know simple equations are, well, simple. But as they get more and more complex, is there always a perfect, precise answer just waiting for us? Or do we eventually have to just settle for close enough?
All right, so to really get why this new idea is such a huge deal, we've got to go back and understand the original problem. For centuries, one of the biggest quests in all of algebra has been finding the roots of these things called high-degree polynomials. So what is a root? You can think of it like a secret key for an equation. When you plug that one specific number into x, the whole thing magically balances out to 0. For a simple equation, that key is easy to spot. But for the really gnarly ones, it's buried deep.
So for a really long time, the usual ways of finding these hidden roots, well, they've had a pretty major weakness. They can get you into the right neighborhood, sure, but they can't always point you to the exact house number.
Basically, these old-school methods are like a super sophisticated guessing game. They make a smart guess, see how close they are, and then make a slightly better guess, and then do it again and again. This gets you an estimate, yeah, an answer that's close. But because of tiny rounding errors, they can't always promise you the exact value.
Here's probably the best way to think about it. An approximation is like a blurry photo. You get the general idea, right? But you're missing all the important little details. A symbolic solution, on the other hand, is like a crystal clear, high-res photograph. It gives you the precise truth, no question about it.
And this is where it gets really interesting. The source material for this new method makes a seriously bold claim. It's saying it can even get around huge historical roadblocks, like Abel's impossibility theorem, which basically proved way back when that some types of polynomials are just fundamentally unsolvable with a simple formula.
So you can see there's this huge split in how you approach the problem. On one side, you've got the traditional way, estimating, which always has that little risk of error. But on the other, you've got this new claim of getting an absolutely precise answer through a totally different symbolic process.
So what is this new approach? Well, it's called Ezouidi's theorem, and it's being put forward as a way to find those crystal clear, high-resolution solutions.
The key thing to get here is that this theorem isn't about guessing with numbers. Not at all. It's about working with the symbols themselves, the x's and the coefficients, using this looping, recursive process to basically force the exact answer out into the open, even for problems that were once thought unsolvable.
So how in the world does it work? Well, the formula itself looks pretty intense, I'm not going to lie. But the idea behind it is actually surprisingly clever. It's all about breaking a giant problem down into a bunch of smaller, repeatable steps.
Okay, so this beast right here, this is the engine of the whole thing. The best analogy is to think of it like a set of Russian nesting dolls. To find the big answer, it first solves a tiny piece of the problem. Then it uses that answer to solve the next piece, and so on, building the final solution from the inside out.
So that crazy-looking formula really just boils down to a pretty straightforward 4-step recipe. First, you set up the equation using symbols. Then you grab the actual numbers from your problem and feed them into that recursive formula. That engine then starts calculating new values, step by step, until it finally gives you the exact roots. No guesswork involved.
All right, theory is great and all, but let's see this thing actually do something. We're going to use a super simple example from the source material just to see how this whole symbolic process actually works.
Yeah, I know. We can all do this one in our heads, right? The answer is obviously 4. But hang on. The point here isn't to get the answer, it's to see how the machine works. Using this simple problem lets us follow the steps without getting bogged down in crazy math.
Okay, so step 1. The process just grabs the numbers straight from our equation. There's a 1 in front of the x, and there's a -4. These become the starting ingredients for our recursive engine.
And now, the magic happens. This is the recursion kicking in. The formula takes those starting values from the first step and uses them to automatically calculate the next value in the sequence. See? It's not guessing. It's methodically building the answer, piece by piece.
And what does it spit out at the end of the process? Bam! 4. Not a round 4, not 4.00001, but the one exact perfect answer.
And this quote from the source really just nails it, doesn't it? The whole system is designed from the ground up to give you certainty.
to get rid of those tiny, annoying errors that can creep in when you're just approximating.
So you might be thinking, okay, why all the fuss? Almost right is usually good enough, isn't it? And yeah, if you're, measuring a piece of wood for a bookshelf, maybe. But when you're talking about science, engineering, it's a completely different ballgame.
Being able to find the exact answer has absolutely massive implications. I mean, think about it. When you're calculating a spacecraft's path to Mars, a tiny rounding error at the start can mean you miss the entire planet by millions of miles. That's why precision is everything. It gives you certainty for scientific proofs and builds a rock-solid foundation for any complex system that relies on math.
And that really leaves us with this final thought. If a mathematical barrier that's been standing for centuries can be challenged like this, it kind of makes you wonder, right? What other impossible problems out there in science or technology are just one new idea away from being solved for good?